Hello and welcome back. Solving linear non-homogeneous recurrence relations with constant coefficient. Please watch my previous video called linear homogeneous recurrence relations before watching this one. It's very important that you watch the previous one so that you can understand this one much better. What is a linear recurrence relation of degree k with constant coefficient? It looks like this. Now, you have two possibilities. If Fn is 0, it's called homogeneous, and that's what we covered in the previous video. If Fn is different than 0, it's called non-homogeneous. Terminology. So when it's non-homogeneous, we're going to use this NHRR, non-homogeneous recurrence relation. And this is the associate homogeneous recurrence relations. In other words, we took this one out. This is the associate homogeneous recurrence relation. Example, this is a non-homogeneous recurrence relation because I have this term here. If I take this term out, I get what we call the associate homogeneous recurrence relation. Same thing here. This is a non-homogeneous recurrence relation. That's of degree. This one is of degree 3 terms here. This one is of degree 2. And the associate homogeneous recurrence relation is this one here. So we took this one out. Introduction. Let's take this non-homogeneous recurrence relation, very simple one we started with, and we're going to show that an is n times n 2 to the power n is a particular solution of this non-homogeneous recurrence relation. So to show that, we just need to substitute in this non-homogeneous recurrence relation. So when you take the right-hand side, okay, and here right-hand side, and we're going to replace this here. So you have n minus 1, 2 to the power n minus 1, plus 2 to the power n. So when you multiply 2 by this, makes it the same power as 2 to the power n here. So you have n minus 1, 2 to the power n, plus 2 to the power n. Obviously, this is n 2 to the power n, which is the left-hand side. Now let's find the general solution of the associate homogeneous recurrence relation. Characteristic equations: R is equal to 2. The general solution of the associate homogeneous recurrence relation is this one here, and all of this are covered in my previous video. That's why I really recommend that you watch that one first. So that's the general solution of the associate homogeneous recurrence relation. Now, if you add them together, you add the general solution of the associate homogeneous recurrence relation plus a particular solution of the non-homogeneous recurrence relation, you get all the solutions. So those are all the solutions of the non-homogeneous recurrence relation. So we can verify that very easily. Again, the right-hand side here is the right side of this here is 2. an minus 1, an minus 1 is alpha 2 to the power n minus 1 plus n minus 1 2 to the power n minus 1 plus 2 to the power n, the right hand side of this, okay? So now you notice that if I multiply 2 here and here, they all become power of 2 to the power of n. So I get alpha 2 to the power n plus n minus 1 2 to the power n plus 2 to the power n. You add them, this cancels this, you get alpha 2 to the power n plus n 2 to the power n, which is the left hand side. So when you replace this in the left hand side, okay, that's the left hand side. All right, so now we move on. Here's the important theorem. The general solution of the non-homogeneous recurrence relation is the general solution of the associate homogeneous recurrence relation plus particular solution of the non-homogeneous recurrence relation. What we know how to solve this. We know how to solve this. This one here, we know how to do it in very limited cases. In very limited cases. And we will discuss some of them shortly. So again, the general solution is the sum of two parts. The general solution of the associate homogeneous recurrence relation plus a particular solution of the non-homogeneous recurrence relation. This one we know how to do. This one we know in some cases. We're going to see some examples. And then what we mean by general solution is we mean that all solutions. Sometimes you hear the term all solutions. That means the general solution. Okay, let's take an example now. Find all solutions of the non-homogeneous recurrence relation. And now here also I give here a starting point, initial condition here. So now again, you see this one here is non-homogeneous because of this term here. To solve this, we need to find a particular solution of all of this here, plus a general solution of this only. Okay, let's see how that's done. Two steps. Step one, find the general solution of the associate homogeneous recurrence relation, and we just did that before. And we know this is the one solution, the general solution of this. Step two, we need to try to find a particular solution of the whole thing now, the non-homogeneous recurrence relation. Okay, let's see how that's done. Now, since Fn is n minus 7, so a reasonable trial solution is a polynomial of degree 1, like to match this. So we are going to try a Tn an plus b as a particular solution of all of this here. And then a and b are constant to be calculated, to be found, to be determined. So substitute in the non-homogeneous recurrence relation. So we take this and we substitute right here. So an plus b here, twice an minus 1 plus b plus n minus 7. So now we are just kind of expanding this. Again here. Now, what I did in this here in this situation, I took all of these terms to the left-hand side, and I put the coefficient of n is minus a minus 1, and then the constants are 2a. This comes here, becomes 2a. Minus 2b plus b is minus b, plus 7 is equal to 0. When you want to have this equal to 0s for all n, you need to make this 0 and this 0. Okay. So we put that's 0 and that's 0, and then now we solve this system of equations, and we get A to be -1 and B equals to 5. So now Tn is -n plus 5 is a particular solution of the non-homogeneous recurrence relation. And now by the theorem that we just mentioned, before that, this is another way of finding A and B. I prefer this way actually, and I'm calling it easier. So you leave you leave all these terms on the right hand side, and you leave all of this on the left hand side. And then what happened is I put some color here. This is all the coefficient of n. Here are the constants. The n here has two coefficients, 2a plus 1, see? And then the constant. And now I match this with this and this with this. That's easier than the previous way we did it. So you match this. Now you can solve this. You get A equals to -1 and B equals to 5. So Tn is -n plus 5 is a particular solution of the non-homogeneous recurrence relation. Therefore, the general solutions, all solutions are, see, the sum of these two, the general solution of the associate homogeneous recurrence relation and the particular solution of the non-homogeneous recurrence relation, which we just calculated. Now use the initial condition, A1 is equal to -3. So you put, when n is 1, -3, you put 1 here, you get 2 alpha minus 1 plus 5. You get alpha to be equals to -7/2. And then the solution with the initial condition is this here. Now you can check your answer if you want. We need to show that this is the solution or all solutions of the non-homogeneous recurrence relation. This verification, you have an minus 1 is an minus 1 is -7/2 to the power n minus 1 minus n minus 1 plus 5. The right hand side now is this. You substitute, you get all of this here. And just add them together here. And you see that you get the left hand side. Just by kind of simplifying here, you get the left hand side. Now it's really easy to show that A1 is equal to -3. Here, if you put here n is 1, you add this here, you get -3. Example 3, let's do that now. That's I'm giving you more examples. Find all solutions of the non-homogeneous recurrence relation. Again, we will find the general solution of this alone, and then a particular solution of the whole thing here. Okay? 2 steps again. Find the general solution of the associate homogeneous recurrence relation, which I'm using the same one here because of the, it's easy now to start easy examples. And we know that's the general solution. Now we try to find a particular solution of the non-homogeneous recurrence relation. And since this one is polynomial of degree 2, so we will try to find a particular solution as a polynomial of degree 2. So we set it up this way. So this is a polynomial of degree 2. Now A and B and C are unknown constants to be determined. Okay, so we have to determine these constants. So we replace this in the non-homogeneous recurrence relation here. You get this. Okay, we just replaced it here. Tn, this one here, Tn minus 1 plus n squared minus 12. So now I am putting all terms, coefficient of n squared, coefficient of n, and the constant. I'm leaving everything on, I'm leaving those in the right-hand side and those in the left-hand side. Okay, I'm not combining them as of yet. So now with colors, you see what I did. This is n squared, this is n, that's constant. So I'm going to match A with this, B with this, C with this. Okay, very simple. You solve this system of linear equations and you find A minus 1, B minus 4, C 6. So this is your particular solution of the non-homogeneous recurrence relation. That means now all solutions will be the sum of this plus this. Alpha is an arbitrary real number. Number 4, example number 4, find all solutions of the non-homogeneous recurrence relation. Again, I kept this for now because I'm just kind of giving you examples here. We'll do more later on. So 2 steps, find the general solution of the associate homogeneous recurrence relation, which we know it to be alpha times 2 to the power n. Now find a particular solution of the non-homogeneous recurrence relation. And since this is polynomial of degree 2 times 5 to the power n, we will try, we're not sure we'll succeed, we will try to find a solution of this form. Polynomial of degree 2 times 5 to the power n. A, B, and C are constants to be determined. Okay? We take this one and substitute it in this recurrence relation. Okay, just a substitution. Now I'm going to group the terms, powers of n squared and n, so that we can match later on. So I did all these calculations. And now I'm going to do with colors. Okay, so you see, now you match A with this, you match B with this, you match C with this. System of 3 equations. I can simplify it this way. You solve it, you get A minus 5 over 3, B minus 20 over 9, C minus 470 over 27. So not all the time you get some nice numbers here. Sometimes you can get really fractions like this, some complicated numbers. So Tn will be the particular solution of the non-homogeneous recurrence relation. And therefore, the general solution or all solutions are the particular solution here, plus, this general solution plus the particular solution. Okay, now we're getting a little bit a different example here. We have now a recurrence relation of degree 2 now. Okay. And here are the initial conditions. I have 2 because I have a degree 2 here. And find the first, we need to find all the solutions. We need to find all the solutions. We have to find first the general solution of the associate homogeneous recurrence relation. And again, as explained real well in my previous video, you first write the characteristic equation. Solve the characteristic equation. You find 2 roots, in this case, -3 and 5. So the general solutions of the associate homogeneous recurrence relation is alpha 1 minus 3 to the power n plus alpha 2 5 to the power n. Alpha 1 and alpha 2 are any real numbers. Now we need to find a particular solution of the non-homogeneous recurrence relation. Again, since here 7 to the power n is the Fn, so we will try to see if Fn 7 to the power n. So we will try to see if C times 7 to the power n might be a good choice, and C is a constant to be found, to be determined, if any. So this is the non-homogeneous recurrence relation, and now we are substituting this particular solution in here. Now, I want you to notice that here I have 7 n to the n minus 2. This is 7 to the power n, 7 to the power n, 7 to the power n minus 1. I need to make all of this the same power. So I have here to divide by 7 and multiply this by 7. Here I have to divide by 7 squared and multiply this by 7 squared. Okay, that's what I'm doing. You see now what happened here? Let me just clean this up so you can see it better here. So okay, so you see here what I did. I divided by 49 and I multiplied this by 7 squared. Now you can cancel this, 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 and this. I don't know why it's stuck now. Okay, so so you simplify 7n, 7n, 7n. You do all of this here. It's just kind of calculation, not really much. And you find C to be 49 over 20. So now we have the particular solution of the non-homogeneous recurrence relation is 49 divided by 27 to the power n. Therefore, all solutions are, see, the general solution of the non-homogeneous recurrence relation, the associate, to the associate homogeneous recurrence relation, and this one is the particular solutions of the non-homogeneous recurrence relation. Now we need to find alpha 1 and alpha 2, so now we need to use the initial conditions. That's ignoring the initial conditions. We get this. Now we need to use the initial conditions. So we just A0, we know it's 1 and A1 is negative 11. We substitute there, and we need to solve a linear system of linear equations, 2 equations. You find alpha 1 equals minus 209 over 80, and alpha 2 minus 65 over 16. Therefore, what we are looking for, the solutions of the non-homogeneous recurrence relation with initial conditions, is this one here. Example number 6. I want you to try to stop the recording and look for a particular solutions of the non-homogeneous recurrence relation. Just the particular solution. So, welcome back. Here's the, consider the associate homogeneous recurrence relation. That's this one here. We know the characteristic roots are -3 and 5 from the previous example, okay? And that's important to notice here, okay? I want you to notice this here and this here. So let's try C times 5 to the power n as a solution, a particular solution. You substitute. Again, you see here I have to divide by 25, which is 5 squared. Here I have to divide by 5 to make this and multiply by 5. Then 5 to the power n will be in all terms. Okay, that's what we will do. See how I divided by 25, then 5 to the power n, divide by 5. Now you can simplify. And you find C is equal to C plus 1, which is impossible. Maybe that's what you found out. Impossible because 5, which is in here, is one of the roots of the characteristic equation. So we need to do some modification. Now try, instead of C times 5 to the power n, try C times n times 5 to the power n. And if you really watch my previous video, you will understand what we're doing here, why we are adding an n here. So we keep going here. So now you replace it, you substitute. Again, you have to divide by 5, multiply by 5, divide by 25, 5 squared, multiplied by 5 squared, so that you can simplify. Again, you see here by 5, 25, and then keep going. Keep going, and you find now C is equal to 5 over 8. So now we are good. We solved it. Then Tn is equal to 5 over n, 5 over 8 times n times 5 to the power n. And that it does it this time. Okay, so let's see some more examples. Now it's your turn. Find a particular solutions of the non-homogeneous recurrence relation. This one is of degree 3, as you can see, of degree 3. So pause your recording and try to do it on your own and come back to see if you succeeded. Okay, welcome back. Let's see what happened, what you did. The associate homogeneous recurrence relation is this one here. The characteristic equation. The characteristics rules are 2, 2, and 2. So that's a root of multiplicity 3. Okay, so R equal to is a root of multiplicity 3. Fn is, since Fn is, see, Fn is this one here, is 18 times 2 to the power n. So a reasonable trial solution is, see how I added n cubed here, because 2 is of degree 3. 2 is of degree 3. And we're going to find the constant C. Try this. All right, now C again here. This is 2 to the power n here, 2 to the power n here. I need to make this one 2 to the power n. I need to make this one 2 to the power n. I need to make this one 2 to the power n. So you divide this by 2, multiply by 2. Here you divide this by 9, which is 3 times, by 4, because that's 2 times 2. And multiply by 4, and you divide this by 8, which is 2 times 2 times 2, and multiply by 8 to make this 2 to the power n. That's what we're doing. When you divide this by 2, you get 3. When you divide this by 4, you get 3. We divide this by 8, you get 1. Now you can simplify this one here, this one, this one, this one, this one. Okay, and now we're just grouping terms. So if you group the terms here and you really find that See, that's, you have n cubed here, you have here 3n cubed, here 3n cubed minus 3n cubed cancels, the blue cancels. So just do some simplification here, and you find that 0 is equal to negative 6c plus 18. So it so happened that the n cubed, all of these terms cancel each other's. All of these terms here cancel each other. So you get this here. And now c is equal to 3. And we found the particular solution of the non-homogeneous recurrence relation. Now, here's a lemma 1. If T1n is a particular solution of this, and T2, T sub 2, C sub 2, n is a particular solution of this, then if you add them, you have a particular solution of the addition of these two recurrence relations. So if you add them, you will have a particular solution of this. Okay, and that's very useful result here that we need to use. How to prove this is very simple. They substitute T1n, T2n, add them, and you find that they are solution to the addition of the two non-homogeneous recurrence relations. Theorem 2. Now, this is the important theorem now. If Fn is a polynomial of degree k times beta to the power n, k is an integer positive, non-negative, and beta is a real number, then what happens? Then a particular solution of the non-homogeneous recurrence relation Tn is polynomial of degree k times beta to the power n if beta is not a root of the characteristic equation. Characteristic equation of the associate homogeneous recurrence relation. Otherwise, it's polynomial of degree k times n to the power m if beta is a root of multiplicity m of the characteristic equation. Okay, of the associate homogeneous recurrence relation. So let's see how we can use this. And we have been using it. POLY, we call that as a polynomial. Here, what form does a particular solutions of this non-homogeneous recurrence relation have when, note, 5 is really a root of the characteristic equation of multiplicity 2. We know that if I solve this, I find the root 5 is a root of multiplicity 2. Now look at those cases. If Fn is 5 to the power n, pause and solve it and see if you can find what form the particular solution will be. Here's the answer, is polynomial of degree 0, because I don't have polynomial here, which is like a constant, and then n squared times 5 to the power n. Why n squared? Because 5 is a root of multiplicity 2. Now this one, pause and solve. Let's see now what you got. Polynomial of degree 1. So I will have a polynomial of degree 1. 5 is a root of multiplicity 2. And look what happens. Polynomial of degree 1, n squared times 5 to the power n. Another example. Pause and solve. Let's see what you got. Polynomial of degree 2. So it will be polynomial of degree 2 times n squared 5 to the power n. Here. Pause and solve. Okay, see what happened now. See, this is n squared, so you will have polynomial of degree 2, but 7 is not a root to the characteristic equation. Then you don't multiply it by any powers of n, so that's what you get. Now, your turn again. What form does a particular solutions of the non-homogeneous recurrence relation, where, look at that now, 3, 3, 5 are the roots of the characteristic equation of its associate homogeneous recurrence relation. So pause and solve and see if you get it right. Okay, we'll come back. Let's see. Notice that you have this is, and this is, and this is separate. Or each one of them will give me one particular solution, and then we add them up. Here, remember 3 is of multiplicity 2. Then you will have polynomial of degree 1 times n squared times 3 to the power n. This one here, 5 is also is a root of multiplicity 1. Then you get polynomial of degree 3 times n times 5 to the power n. And here is no problem because 7 is not a root. You get polynomial of degree 2 times 7 to the power n. And here's what you see. N squared here because 3 is of multiplicity 2. N to the power 1 because 5 is a root. And here there's no n here because 7 is not a root of the characteristic equation. This is very important now. Some students confuse this and gets it wrong. If Fn is a polynomial of degree k, only polynomial of degree k, now you would imagine that there's a 1 here to the power n. You can imagine that. So now a particular solutions of the non-homogeneous, see here, is polynomial of degree k if 1 is not a root of the characteristic equation. Excuse me. And n to the power m if 1 is a root of multiplicity m of the characteristic equation. So you pay attention to this special case when 1 is hidden here, it's not there, okay? So here, example 10, I think that's maybe my last example. Pause and solve and see if you can find the particular solution in this case. Okay, we'll come back. Let's see what happens. Now you would imagine, okay, that there is 1 to the power n here. Okay, so see what happens. That's first one, nothing. Polynomial of degree 1 times 3 to the power n, because 3 is not a root. The second one, 5 is a root, so that's why we multiplied n to the power 1 by 5. Now the third one here is polynomial of degree 2, but 1 is a root of multiplicity 2. That's why we put n squared. So as if you have n squared times 1 to the power n. So you pay attention to this. Be careful when that happens. That's very important. And I hope you enjoyed this video. Please subscribe if you have not done it yet, and I will see you soon. Thank you and goodbye.